Welcome back. In today's system design session, we're diving into the architecture of large-scale object storage systems, the backbone of modern cloud platforms like Amazon S3, Google Cloud Storage, and Azure Blob Storage. These systems store everything from personal photos to billion object data lakes for enterprises. But how do they manage petabytes of data, support millions of users, and still deliver on SLAs like 11 nines of durability? In this video, we'll break down the end-to-end design of such a system, from high-level architecture and API flows to internal storage layouts, metadata models, replication strategies, and more. By the end, you'll understand what it takes to build an object store that is durable, scalable, and production-ready. Let's begin by framing the problem. The problem is to design a large-scale object storage service like S3. Here are some good requirement questions to ask. Which features should be supported? What's the typical data size? What are the SLAs of durability and availability? In this slide, we walk through the architecture and flow of a cloud-scale object store, similar to Amazon S3. The core principles driving the design are object immutability and write once, read many semantics. That means once an object is written, it is never modified in place, ensuring consistency, integrity, and simplified replication. Key features and requirements. The system must support both small and large objects efficiently. For instance, a few kilobytes of logs or several gigabytes of video content. All operations are exposed through a RESTful API service, supporting standard methods like PUT for upload and GET for download. IAM, Identity and Access Management, ensures each request is authenticated and authorized based on permissions tied to users, roles, or buckets. Storage components. The metadata store is responsible for managing bucket-level and object-level metadata, like object names, sizes, UUIDs, timestamps, and access policies. This is typically implemented using a fast, highly available database. The data store is a key-value store optimized for durability and high-throughput object reads, writes. Each object is stored against a unique UUID, object upload flow. The client sends a PUT request to create a bucket. The API layer authenticates via IAM and stores the bucket metadata. Once the bucket exists, the client can put an object. The API forwards the object payload to the data store, which stores it and returns a UUID. The API then writes an entry into the metadata store, linking the UUID to the bucket name and object key. Object download flow. The client sends a GET request to the API through a load balancer. The API service authenticates the request, looks up the object's UUID via the metadata store, and retrieves the data from the data store. The object data is returned to the client in the response. This design emphasizes separation of metadata and data paths, enabling efficient scaling and flexible data management. It also enables fine-grained access control, which is essential for multi-tenant cloud storage platforms. Now let's dive into the architectural internals of our object store system, focusing on how we store, organize, and maintain object data at scale with durability and efficiency in mind. 1. Data store architecture. We start with the data routing service, which acts as a stateless entry point for storage operations. It doesn't persist data, but orchestrates where data should go. To determine placement, it contacts the placement service, which knows the health and load of all data nodes. Based on this, it selects a primary data node and one or more secondary nodes for replication. The object data is first sent to the primary node, which writes the data locally and replicates it to secondaries. Only after successful replication does it return a success acknowledgement. This replication ensures durability and availability. Each object gets a UUID, and the UUID is returned to the API layer for metadata updates. 2. Object layout and space efficiency. Storing each object as a separate file leads to space inefficiency, especially for many small files. To address this, we implement a write-ahead log, WAL style file layout. Small objects are appended to a large container file. When it reaches a size threshold, it's sealed, read only, and a new file begins. This reduces the file system's overhead and boosts disk I/O efficiency. For retrieval, we maintain an object mapping table, indexed by UUID, that tells us which file the object is in, along with its offset and size. This can be implemented using a lightweight relational DB. 3. Durability techniques. In addition to replication, we support erasure coding for long-term storage. This technique chunks data and adds parity segments. It provides the same durability guarantees, but with less storage overhead than full replication. We also use checksums, e.g., MD5 or CRC32, to verify the integrity of objects during both write and read operations. 4. Metadata schema. Metadata is stored separately and includes two main tables. The bucket table, storing configuration like owner ID and versioning settings. The object table, storing the object's UUID, name, version, and bucket association. We shard metadata by bucket name, object name for better scalability. To mimic directory-like structures, we allow prefix-based object organization, letting users query or group objects by virtual folders. Versioning is handled by inserting multiple records per object name, each with a new version and object ID. The current version is simply the one with the highest object version number. 5. Multi-part upload. For large files, we use a multi-part upload protocol. The client initiates an upload and receives an upload ID. The file is split and uploaded in parts. Each successful upload returns an E-tag, checksum. After all parts are uploaded, the client sends a complete request with part metadata. The data store then reconstructs the object and finalizes it. This allows for resumable uploads, parallelism, and better fault tolerance. 6. Garbage collection and compaction. Finally, we must clean up unused storage. Lazy deletions, incomplete uploads, or crashed writes may leave orphaned data. A background garbage collection service periodically scans for and reclaims such space. We also run a compaction process to merge fragmented files and reclaim capacity, especially in WAL-based storage. This deep dive reveals how a production-grade object store must balance performance, cost efficiency, and strong durability guarantees, especially at the scale of billions of objects.